Foundation models like Prithvi can now interpret satellite imagery at a level that just wasn't possible 5 years ago. But they run on the ground. Data are processed days or even weeks after capture. For an application like land degradation, this delay can really matter. The opportunity here is to bring the AI onto the satellite. Real-time analysis in orbit. Satellite is a 6U CubeSat on Charan Orbital Triumph bus. It hosts a Samara Multiscape 100 visible near-infrared spectroradiometer with 4.75 meter ground resolution, and then it transmits 200 byte alerts instead of 160 megabyte scenes, which is a 98.7% data reduction. This is what we demonstrate with SoilSentinel.
I'm Sandupal from Johns Hopkins University. SoilSentinel's decision-making is powered by NASA's data integration. At its core is Prithvi, a foundation model pre-trained by NASA and IBM on the harmonized Landsat Sentinel archive. To detect anomalies, we integrate Modi's vegetation baselines into the vegetation condition index, a standard used by NOAA, enabling the system to identify precisely vegetation stress and soil erosion risk. By monitoring the bare soil index alongside NDVI, we derive an eco-erosion risk index. As the video demonstrates, as soon as the NDVI greenness plunges and rainfall event occurs, the bare soil scar expands, marking the spectral signature of active soil erosion.
Hi, I'm Víctor Tenorio from King Juan Carlos University in Madrid. Prithvi has 300 million parameters, far too much for any CubeSat. With knowledge distillation, we are able to compress that more than 300-fold. The student learns directly from Prithvi's predictions, inheriting its understanding of the grading land, and when evaluated on how well it predicts future BSI and NDVI indexes, it maintains 85% of its performance in terms of R-squared. Distillation also makes the students robust to sensor noise. When evaluated using noisy data, it drops less than 2% of accuracy versus when evaluated on clean data. On board, the student predicts soil health weeks into the future and triggers an alert when erosion risk is high, sending a compact packet to the ground to apply preventive action. We are able to save with this over 95% of the bandwidth while correctly flagging 89% of in-risk pixels.
We validated SoilSentinel using up to 800 gigabytes of NASA harmonized Landsat and Sentinel-2 multi-temporal data across agriculture and post-fire land degradation. We also performed an expert-led cold outreach for market discovery, building on completed interviews and ongoing discussions to validate real-world feasibility. Our highlights are that soil degradation drives roughly 400 billion in annual losses, while current monitoring remains reactive and relies on delayed processing. The key insight is that value comes from high-frequency field-level alerts every 3 to 5 days, using not only proactive approaches but also preventive ones.
We compress NASA's best AI to fit on a satellite. The question now is what problem we solve first.